Hey everyone, welcome back. Today I'm going to continue talking about regression and go through a kind of a grab bag of different topics related to regression following on from last week's lecture where I talked about linear regression in a little bit of detail last lecture. You might want to do higher order polynomials. You might want to regress a quadratic or a cubic curve through your data. And so how do we do polynomial regression? Well, if you know how to do linear regression, it's really simple. You just take linear regression and you add polynomial features, as we discussed in lecture 4. So you're given a bunch of sample points, xi, and we just replace each xi with a longer feature vector. Recall that our notation from lecture 4 was capital Greek letter phi applied to xi. And the idea is now we're going to use all of the terms of degree 0 through p, where p is the order of the polynomial we want to use. So, for example, phi of xi, suppose we want to do quadratic regression, and suppose that there's only 2 features for each sample point. Then we need all the quadratic features in the 2 variables xi1 and xi2. And we need all the linear features. And we also need the degree 0 feature, which is basically a constant. We usually use the number 1. And that number 1, that is the same fictitious dimension that we used last lecture. So we still have this idea of a fictitious dimension that allows us to have a regression function that is not 0 at the origin. But now we have also quadratic, linear, and 0 order terms. And that allows us to fit an arbitrary degree 2 polynomial to our data. Otherwise, this is just like linear regression. We can take the linear regression algorithm that we discussed last lecture and just reuse it on these length and feature vectors. Also, we can do this for logistic regression as well. So it's permissible to modify logistic regression to make it more expressive by adding quadratic features. And if you do that, if you take logistic regression and you add quadratic features, as I've just shown you, then the posterior probabilities that you get by regressing have the same form as the posterior probabilities in QDA. So just as logistic regression in its standard form is a natural counterpart of LDA, logistic regression with quadratic features is a natural counterpart of QDA, where we say, what happens if we take the same form of posterior, but we just fit it directly to the data instead of constructing models of the input classes? Now, one thing that's nice in talking about polynomial regression is that you can learn a lot about what can go wrong with polynomial regression just by looking at one-dimensional examples, one-dimensional feature spaces. And the big problem is that as the degree of your polynomials increases, it becomes very easy to overfit the data. Pardon me. And this is something that's pretty easy to see even in one dimension. So let's take a look at some examples of polynomial regression in 1D and get a feeling for some of the things that can go wrong. All right, so this first example, what is going on is that there is an underlying true relationship between x and y. So the horizontal direction is just our one-dimensional feature space. The vertical dimension is the labels we want to interpolate or the hypothesis over x1, either way. And the ground truth that we're trying to replicate is the black curve. So if you look at, that's not it. If you look at this curve here in black, that is a third-order polynomial. And imagine that that is the ground truth. So this is the correct expression of how the data is generated, but there's noise in the data. So the actual data points you can see are these round circles, and they don't lie exactly on the ground truth curve because they have added noise. So these black circles here, those are the data that we want to fit. So let's see what happens if we try to fit this with second-degree polynomial regression, fourth degree, sixth degree, and eighth degree polynomials. So the second order fit is the red curve. So if you look at the red curve, you can see that it is not a very good approximation to the black curve. It's just very hard to fit a cubic data with quadratic curve. Not surprising. So that is a clear case of underfitting. The red curve just doesn't have enough flexibility to hit the data. But when we go to a fourth order curve, so the green line is 4, you can see the fourth order curve looks like this. And actually fits the data pretty well, fits the black curve, the ground truth, pretty well. Not surprising, a fourth order curve can do a good job of approximating a third order curve. But what happens if we try increasing the polynomial degree further? Well, things start to go wrong because we start to see overfitting. So the sixth degree curve is blue. So a sixth degree polynomial, you can see it here's the sixth degree curve. You'll notice it's starting to oscillate more. It oscillates more than the fourth order curve in green, and it actually isn't as good a fit to the black underlying ground truth curve as the fourth order curve is. And then, of course, if we go up to eighth order, things get even worse. Look at this eighth order curve in yellow. Look at how it starts to oscillate like crazy. That's really not a good reflection of ground truth. And this kind of oscillation is naturally what usually happens when you have high-degree polynomials and you try to fit them to data. Unless you do something to control that oscillation and stop it, you're going to get something that's not very accurate in places like there, where it's just crazy. And this can get more and more extreme, so let's see what happens if we go to a degree 20 polynomial in one dimension. And this is being fit to just over 20 data points, 21 or 22 or 23 or something. Look at that oscillation. That is obviously useless. That is obviously not going to be a good data model for any purpose whatsoever. Even though it goes exactly through all of the blue points. I have another example here, which I think shows you something more subtle. So what this is US population data over a period of time. So the horizontal axis is the year. And you'll notice 1900, 1950, 2000, 2050. So we are somewhere around here. And the data points are in blue, so you can see up to there. That's the data we use for interpolation. And the fitted curve that we've fit here is a degree 4 polynomial. So you might ask, is this a good interpolation? Not really. There's something wrong with it. It seems to think that in the year 2050 we're all going to be dead. So what went wrong? What went wrong is essentially the fact that we're doing what's called extrapolation, meaning we are trying to interpolate outside of the region where we have data. Needless to say, extrapolation is pretty hard. It's as hard as predicting the future, in a way. And most learning algorithms aren't very good at extrapolation. It's just really hard to be good at extrapolation. Yes?
Is there a way to see how well we're fitting the data plus how much we're overfitting? Or this eye test looking at the fluctuation?
Oh, how do we see if we're overfitting? That's what validation is for. So the usual procedure, we hold back validation data and we interpolate to the stuff that we haven't held back, and then we do check if it's correct on the validation data as well. And that is how you would choose what order of polynomial, what degree of polynomial you want to use. Does that answer your question?
So also, it's like the degree we're choosing is also a hyperparameter.
Yes, you should think of the degree of the polynomial as a hyperparameter and choose it by validation just like any other hyperparameter. That's right. Mm-hmm.
Yeah, you mentioned there might be a way to discourage the overfitting without just choosing a simple model as long as the data are expand on it.
What other ways could we reduce overfitting? The simplest way is something that's called regularization, which we will talk about in detail next Monday. But the short version is that you just penalize large weights and solve a model where large weights are penalized, and that tends to reduce overfitting. The other thing is, if you dive more deeply into interpolation theory, if you have points in very carefully controlled locations, which are zeros of Chebyshev polynomials, you can actually get polynomial interpolation degree to be very stable. But that requires that you have some control over where your data points are located, and we don't always have that, so that's tricky to use. All right, I want to show you one more example of high-degree interpolation that doesn't fail. But the reason it doesn't fail is because there's so much data that it works. And so, well, let's look at the figure on the left first. Ignore the one on the right for a second. So what we're doing here is all that blue smudge, those are training points. And you can see that there's a great deal of noise, and like random values have been added to each Y label. But there's a lot of points, so that helps to make up for all that noise. And they show what happens if you fit a degree 1, degree 3, or a degree 10 polynomial to that. So let's look at the degree 10 polynomial, which is this curve here. It's pretty good. It doesn't oscillate like crazy. And the reason it doesn't oscillate like crazy is because there's so much data. There's enough data to tame that degree 10 polynomial and make it look right and not oscillate. You can also see that it does the best job of, with this particular data, of modeling correctly the upward turn in the data at the right end of the spectrum here. So that's an example where a degree 10 polynomial works well. And this on the right, what we have is another example. In this case, though, we're actually doing a little bit of extrapolation as well. So, I am suddenly realizing I don't think I have the correct idea of what they were doing with this right-hand drawing. Okay, I think the point I wanted to make here is not in effect. So forget about this and let me move on. The main point is, here's an example where by having lots of data, we have tamed the degree 10 polynomial and actually gotten a good result. So are there any more questions about this? Yes? Is there a rule of thumb for the amount of data you need for the polynomials? Well, in the one-dimensional case, I'm not quite sure how much data it takes to tame, say, a 10th order polynomial. But my guess is that if you have an order p polynomial, then probably order p to the 3 halves data is about right. So, but that's my guess. I will say, though, that as you go into higher dimensions, you have a problem, which is the amount of data you need is exponential in the number of features. So if you're working in a 10-dimensional feature space, then you need to raise that to the 10th power, because you need to have enough data in each direction in that 10-dimensional feature space. So using high-degree polynomials in high-dimensional feature spaces tends to fail. It's just too flexible, too many parameters. Yeah? Mm-hmm. Right. So what? Well, validation is not a solution to the extrapolation problem. And I don't really know good solutions to the extrapolation problem. Extrapolation is inherently hard, just like predicting the future is inherently hard. People try, and just about everything has failed. So the most likely thing that people do for extrapolation often in classification problems is just nearest neighbor algorithms. Because at least nearest neighbor algorithms are stable. At least a nearest neighbor algorithm is not going to give you, points way up here, because the nearest neighbor points are, well, it has to be one of these, right? It has to be something down there. So at least nearest neighbors usually gives you a sane value, as opposed to a completely insane value. But we have very limited toolbox for doing that because it's inherently hard. Other questions? All right, so we're going to move on to the next topic in our grab bag, which is, just want to briefly present how weighted least squares regression is written out and solved. It's a pretty easy change to standard least squares linear regression. Now, in terms of the menu of options I gave you last lecture, we are using a linear regression function and a squared loss error, just like standard linear regression. But the cost function is modified slightly to put a weight in front of every squared error, squared loss. So again, the idea of weighted least squares regression is that some points might be more trustworthy than others, or some points might be more important than others, that we just want to fit them better for some reason. If we think that there's a lot of error in a point, we might trust it less and want to give it a lower weight. If we think that fitting a point is really important or a point is really trustworthy, we might give it a higher weight. Exactly how you do that is up to you, but what we ultimately do is we assign each sample point some weight that says how important this point is or how much we trust it. And then we collect all those weights into a diagonal matrix. So we have an n by n diagonal matrix, which we'll call capital omega. And reminder, these weights, those are the Greek letter little omega. So that's an omega I, as distinguished from the weights W that the learning algorithm learns, the regression coefficients. So the way that we actually translate that priority into mathematics is that the bigger the value is of omega I, the harder we're willing to work to minimize the squared error. And I'm writing the squared error as the value y hat I predicted for sample point I by the classifier minus the true label yi that we've been given to train on. And just to recall what the definition of the y hat is, there is a vector y hat which is just x times w. Once we've learned the weights w, once we've finished learning the regression coefficients, then we can plug them back into x, the sample points, to find out what our predictions are, what that regression's predictions are on the points we originally trained on. So now we can write our optimization problem. We want to find the weight vector w that minimizes. Here's how we're going to write out the function. We've got xw minus y, but instead of just squaring that, as we would with least squares linear regression and minimizing that, we're going to multiply it by omega times xw minus y. So this is how we get those weights fit in there, is we stick them in between, in the middle of the x squared, so to speak. The xw minus y squared winds up having this matrix omega stuck in the middle. And again, it's a diagonal matrix, so what this matrix multiplication is really computing is a sum over all of the sample points of the weight omega times the squared error for sample point xi. So with a little effort, remembering that big omega is a diagonal matrix, you can prove to yourself that this is equal to this. All right, so just like with ordinary least squares, we are going to solve this by taking the gradient of that thing, that objective function, and setting it to 0. And when you do that, you get a set of normal equations, just like standard least squares linear regression has the normal equations. Here we've got a slightly different set of normal equations. And so the normal equations for weighted linear regression look like this. You'll recall that that's almost the same as standard least squares linear regression. In standard linear regression, these are the normal equations. You just cross out the omegas. If you want weights, then you just add in the omegas. And so you've got these normal equations. Once again, this here is a matrix. This is a vector. We know the values of everything in blue, and we just want to solve for W, which involves solving a system of linear equations. And that's all I have to say about that. Any questions about it? Yeah.
Can we use the same formulation of weighted least squares to achieve the same goal as regularization?
Can we use this to achieve the same goal of regularization? No, it's not quite the same. It's going to be a little bit different. Regularization, yeah, I don't think you can get it into this. Yeah. Xi is a vector. I'm writing a dot product here, so it doesn't really matter whether you transpose it or not. Is that? No, that's an inner product. That's a dot product of two vectors. All right, another abrupt change of topics. In this class, we don't have time to teach you a lot of optimization methods in any detail, but the one that we do talk about a lot is gradient descent. There's one other one that I want to talk about briefly because it's very applicable to logistic regression, and that is Newton's method. And not only is it going to be a way to solve logistic regression quickly, but it also gives us a little bit more understanding about what logistic regression actually does. So that's another reason to teach it. So Newton's method, like gradient descent, is an iterative optimization method, though it only really works well for smooth functions. But if you have a function that is smooth enough, it's often much faster than gradient descent. And as it turns out, the logistic regression cost function is smooth enough for Newton's method to work quite well. So here's the idea of Newton's method. Imagine you are currently standing at a point V in weight space. We are going to approximate the cost function, JW, that we're trying to optimize, in the vicinity of V with a quadratic function. And a quadratic function generally has one unique critical point. If we've If our function is strictly convex, it'll be a bowl. And so we jump to the unique critical point of that bowl. And then we just do this over and over again until we think that we've achieved some measure of convergence. That's the high-level idea of the algorithm. Let's look at some pictures to get a feeling for what that means. All right, so these figures show 3 consecutive steps in Newton's method, 3 consecutive iterations. So the blue curve is the cost function that we want to minimize. And so that curve there. We're looking for this point here, the minimum, basically. Now, suppose that our starting point is right here. So this is the point V where we are currently standing. What we do is we look up at where that intersects the blue curve here. And at that point on the blue curve, we compute the gradient of the blue curve and the second derivative of the blue curve, so the curvature. And based on those 2 things, then we find the unique quadratic curve. So this thing is quadratic, that has exactly the same slope and exactly the same curvature at that point. And the reason we find that is because we want to jump to the bottom of that. We want to jump to right there. So after we finish that, our new point will be there. And then we repeat the process again. So now for the second iteration, we imagine that we are here. And here's the point on the curve, on the blue curve. And again, we measure the slope and the curvature of the blue curve at that point and fit it with a quadratic curve, this parabola here. And again, we jump to the bottom, which puts us here. And we do it again, jump to the bottom, and so on, until we get close enough to the minimum. So that's what Newton's method looks like in 1 dimension. It's a little harder to visualize it in 2 dimensions. It's surprisingly hard to find good plots of this. But here's the best example I could find. Here's a 2-dimensional example of Newton's method. And this is a pretty nonlinear function in the sense that non-quadratic cost function. It's got a lot of weird curves in it. So when Newton's method starts, well, the starting point is here. And the optimum we're looking for is there. And if we don't start very close to the optimum, we might bounce around a lot and before we find it, or we might not find it. But in this example here, we find it. So the first step of Newton's method takes us from here to here. The second iteration takes us down here. The third one takes us up here. Now, when you get to there, you're in a nice situation because now you're kind of in a region close to the minimum where the function is actually starting to look pretty quadratic, finally. It looks like just an elliptical bowl. And so the next step takes you very, very close to the minimum. Once you catch the right bowl, convergence tends to become very fast. But if you don't start off in the right spot, you might bounce around a lot. That's our intuition about what we're trying to do. Now let's look at the math. To work out how to actually do this, we're going to take a Taylor series about the point V. Remember, V is the point where I'm currently standing and want to jump to somewhere else. Yes? Right, a good question. So how do we choose V? In general, for general applications of Newton's method, it can be pretty hard because if you start too far away from the minimum, you might not find it. But some functions are both convex and really nicely behaved. And the logistic regression cost function is one of those. So with logistic regression, we start at 0. If you just start at the origin, it pretty much always gets you where you need to go reasonably quickly. The cost function, that particular cost function is just really nice in that regard. But there's a lot of other methods where it can actually be pretty tricky. Mm-hmm. Does not just mean you have to be continuous. So think about, for instance, the perceptron risk function, which is piecewise linear. That's a continuous function, but the Hessian is 0 everywhere. The curvature is always 0. So Newton's method, you can't apply it at all. You can't build a paraboloid that fits the local curvature because there is no local curvature. So by smoothness, I definitely mean more than just continuous. I mean that the second derivatives have to be pretty well behaved as well. Yeah? So Newton's method can be faster in terms of actual running time, sometimes even a lot faster, but it does depend partly on the dimension of your feature space. So if you have a low-dimensional feature space, Newton's method for logistic regression is likely to be a big win over something like blind gradient descent. If you have a huge dimensional space, if you have 100,000 features, then you have a problem because Newton's method has to compute the Hessian matrix, which is 100,000 by 100,000. So you're kind of doomed. You have to do something simpler and dumber in that case. But for small feature spaces, it can be really fast, like actual running time and number of iterations. So I want to write a Taylor series for grad J. Not for J, but for grad J. And the Taylor series for grad J, if you have a point V that is close to W, then we can write this approximation. Grad J at W is grad J at V plus, here is the Hessian matrix. The second derivative of J multiplied by W minus V plus there is one more term that is some number in, well, some vector in big O of W minus V squared. So the idea here is that we are hoping that W and V are close together so that this is small. For W far away from V, this Taylor series is not going to give us a good approximation. But for W close to V, it does. And this is also small in the range where it works well. And again, this thing here, this notation, is the Hessian matrix of second partial derivatives of the cost function j evaluated at the point V. So what we're going to do is, when I say we're going to jump to the bottom of this paraboloid or jump to the critical point is the point where grad j is 0. So we're going to find our new point W by setting grad j equal to 0 and solving for W. And in order to solve for W, what I'm going to do is I'm going to basically pretend that this quadratic term, W minus V squared, is not only small, but it's so small that we pretend we can ignore it. And then, with what's left over of this equation, we want to set that equal to 0 and solve for W. So when we do that, we get W equals V minus the inverse of the Hessian matrix times the gradient of the cost function at V. All right, so this is an iterative update rule we can use over and over again to take steps closer and closer to the minimum. So we repeat this until it converges to a solution. One thing that I've mentioned before in other contexts is that when you see something like this, you don't usually want to actually explicitly compute the inverse of the matrix. What you really want to compute is just the inverse of the matrix times some vector, which is solving a linear system of equations, which can generally be done much more efficiently than inverting a matrix. Typically, the algorithm we'll use to solve that linear system of equations will be Cholesky factorization or the conjugate gradient method. So what I want to do is I want to take this math and now I just want to write it as an iterative algorithm. And so this is Newton's method. First of all, you need to pick a starting point W, which, as I said, is for some problems is hard, but for some problems 0 works fine. And then we'll repeat the following loop over and over again. We're going to compute an error term, which is a solution to the implied linear system. And the linear system is Hessian matrix of J evaluated at W equals minus gradient of J evaluated at W. And then you just update W by adding this error term. And that's it. That's the whole algorithm. Yeah?
Watching like the assumption that you made, where you assume that W is going to be close to V, especially if you have a function that is highly nonlinear.
Ah.
Watching
Why can I assume that W is close to V, especially if you have a function that's highly nonlinear? Honestly, you can't. There are many, many cost functions where if you have a bad starting point, Newton's method just fails. So I am definitely not saying that Newton's method is a great general purpose algorithm that works unmodified in all situations. It's not. We care about it today because the cost function for logistic regression is really, really well behaved and won't give us trouble no matter what we do. But that's because that's such a nice cost function. It's not generally true. And there are other contexts where Newton's method can be useful, but you have to add all kinds of extra cruft to make it work on harder functions. And in this course, we don't have time to go into that. This isn't an optimization course, but it's a fascinating subject and, something that is worth exploring if you want to go deep into machine learning. Mm-hmm.
Connecting the math to the graphical representation of the method, the quadratic at each of the points on JW,
Uh-huh.
the yellow quadratic curve that was displayed in the graph correlates to the approximation that is aiming to be displayed.
Yeah, that's right. So these brown paraboloids, what those are is at this particular point here, our current iterate, we are computing the Hessian matrix with respect to V at that point. We're also computing the gradient at that point. And so what these curve is representing is simply the unique quadratic curve that has, that has this Hessian everywhere, because the curvature is the same everywhere in that quadratic, and this gradient at this particular point. And so then when we solve that equation that I wrote down, what that does is it actually finds this point here that is at the bottom of that paraboloid. Does that answer your question? Great. So again, to come back and punctuate a few warnings about Newton's method in general, it does not know the difference between minima, maxima, or saddle points. All it does is it jumps to a critical point where the gradient is 0. It doesn't actually know if it jumped to the right critical point, if there's more than one. And for general functions, as we just discussed, the starting point must be somehow close enough to the desired critical point. And so, fortunately, neither of these are going to be an issue with the logistic regression cost function, because the logistic regression cost function is strongly convex everywhere. You're always going to get a paraboloid that's curving upwards. It's always going to be a smile. We're always going to be jumping to the minimum of that paraboloid. And logistic regression is just a nicely enough behaved cost function that regardless of where you start, you usually wind up at the right critical point, or you usually wind up at the minimum of the cost function after enough iterations. So there's a few reasons why Newton's method can be much faster than blind gradient descent for some optimization problems. The first being that when it takes a step towards the minimum of the paraboloid, it jumps exactly to the minimum of the paraboloid. It doesn't just pick a direction and walk some blind distance in that direction. It actually finds the minimum right away. And second, it doesn't always choose the direction of steepest descent. Sometimes it chooses a better descent direction. Those are the advantages. Disadvantages, again, as we discussed, if you have a lot of features, if you have a high-dimensional feature space, then the Hessian matrix is really big. And if it's too big, then the computation time for Newton's method starts to become longer than the computation time for gradient descent. But there are a lot of problems in machine learning where you have only a small number of features, and for those, this is pretty fast. Also, as we discussed, this does require your cost function to be pretty smooth. And I gave the perceptron risk function as an example where Newton's method does not apply at all because you don't have curvature. You have a piecewise linear function. The Hessian is always 0 or it's undefined. And so it's useless for that. Any final questions before I apply this to logistic regression? Why does what? Why does it converge in general? Well, when you read convergence theorems about Newton's method, they always make a lot of assumptions. So if this long list of assumptions is true, Newton's method can be guaranteed to converge. That's unfortunately not a simple topic and one we can't go to in any detail this semester. But it's an interesting topic. All right, so now that we've learned Newton's method, let's go back and apply it to logistic regression. And for that, we're going to need to derive the gradient of the cost function, which we did last lecture. And now we also need the Hessian of the cost function. So let's recall a few things from last lecture. First, the logistic function. Its derivative with respect to gamma is the logistic function times 1 minus the logistic function. And let's recall this notation. For each sample point xi, I'm going to write the predicted value of the label as s subscript I, which is the logistic function applied to xi dot w. And we're going to have s all by itself being a vector that is the predicted values of logistic regression for all the sample points, all the training points. And of course, recall that last week we worked out the gradient of j, and it turned out to be this value here at a point w. And this can also be written in matrix notation. You can get rid of the summation and write it like that. All right, for Newton's method, we need that, but we also need the Hessian. So let's try to figure that out. The gradient of the gradient with respect to w. What I'm basically going to do is I'm going to take this and remembering we're taking the gradient with respect to w. Where is w in that equation? Well, remember, it's in the SI. So the gradient is respect to w. The w is hiding in the SI. We apply standard calculus to this, including the chain rule. And with some effort and thought, what comes out is SI times 1 minus SI times XI transpose. We want to write this without the summation as well. We can write it like this. We can write it as X transpose omega X, where this matrix big omega is a diagonal matrix that has all the S1 minus S's on its diagonal. So that's the Hessian we need to do Newton's method with logistic regression. So one thing I want you to notice about this matrix omega is that it's always positive definite. no matter what the value of W is, it's always positive definite because the logistic function itself, S1, is always a number between 0 and 1 exclusive. And so 1 minus the logistic function is also a number between 0 and 1 exclusive. So the product is always going to be a strictly positive number. So all the diagonals of this matrix are strictly positive, so it's a positive definite matrix. And so that implies that X transpose times omega times X is always positive semi-definite. For all values of W at all points in in weight space. And one reason why this is interesting is that this actually proves what I only could assert before, which is that the cost function for logistic regression is convex. If a function has a positive semi-definite Hessian matrix everywhere in the weight space, then it's convex. QED, proven. So we're very happy about that, of course, because it means that if Newton's method converges at all, it'll converge to a good solution. All right, I'm going to rewrite Newton's method in the context of logistic regression now. So as I said before, the cost function of logistic regression is so nicely behaved, so forgiving, any starting point will do. So in practice, logistic regression codes usually just start at 0. So now our error is going to be the solution to the normal equations. Which for logistic regression look like this. And just a reminder that the x's and the s's are functions of W. And the reason that's important is because W changes every iteration. And so on every iteration, you have to recompute x. You have to recompute s. Oh, you have to recompute it. No, not x. I'm sorry. I'm so dumb. Let me do this again. It is omega, not x, and s that are functions of W. Pardon me. So, in every iteration of Newton's method, W is changing. We're moving to different points in weight space. And so on every iteration, we have to recompute omega, and we have to recompute s before we solve this linear system. Now, one thing you might notice is that this kind of sort of looks like weighted least squares. But it's not exactly the same. There's a very important difference, which is if it were really weighted least squares, there'd be an omega there as well. There is not. So it's not exactly weighted least squares. But there is an omega over here, and that does have kind of an effect of weighting some points as more important than others, albeit in the reverse of the way you would expect. But because of that, because that matrix on the left-hand side is changing every iteration, Newton's method with logistic regression is an example of what is sometimes called iteratively reweighted least squares. Now, again, though, unfortunately, we need to be very, very careful with the analogy because, as I said, if this were truly weighted least squares, there would be an omega there, but there is not. So this has the counterintuitive effect that a small weight in omega causes the Newton iteration to put more emphasis on that point, not less. It's the opposite of what it does in weighted least squares. So what that's going to imply is that misclassified points that are far from the decision boundary are going to have the most influence on this step E. Correctly classified points that are far from the decision boundary have very little influence, and they have little influence because for those, y minus s is close to 0. And points that are close to the decision boundary have a medium influence. So if there are no misclassified points far from the decision boundary, if you're doing kind of a good job, then the points near the decision boundary will have most of the influence. And the correctly classified points far away from the boundary have very little influence. This is different from LDA. In LDA, every point has roughly equal influence. But here, the incorrectly classified points have way more influence. The points near the boundary are second. The correctly classified points far from the boundary have little influence. And so that's going to lead us into a conversation of what are the pros and cons of LDA versus logistic regression. They're very closely related algorithms. Logistic regression, to some degree, is inspired by LDA, the idea being instead of deriving the posterior probability through Bayes' theorem, why don't we just fit the posterior probability directly to the data? And so you might expect these two algorithms to give you identical results, and they don't. They definitely do not. And I just told you some of the reasons why. But let me quickly list what are the advantages of LDA over logistic regression, and then what are the advantages of logistic regression over LDA. Well, first of all, suppose you have two classes that are really well separated, like the red points and the blue points, for the most part, are not very close to each other. When you do that, LDA is very stable because it fits a Gaussian to the red points, it fits a Gaussian to the blue points, and puts a perfect little boundary between them. Logistic regression is actually surprisingly not stable in that case. And by that I mean one or two bad outliers will push the decision boundary around a lot. And that's a consequence of what I just told you, which is that in logistic regression, points that are misclassified and far away from the decision boundary have a huge amount of influence. So if some of those points are wrong, then your method is very unstable. So LDA is better in that particular situation, but I'll show you another situation later where it's kind of flipped. But another nice thing about LDA is that if you have more than two classes, like if you have a 10-class digit identification problem, then it's really easy and elegant to make LDA do a 10-class problem. Logistic regression is not really as good a fit to that. It can be done. There is a related algorithm called softmax regression that tries to solve that problem of doing something like logistic regression with more than two classes, but it's not as easy and elegant. Another advantage of LDA is that it is slightly more accurate when you really do have classes that are nearly normal. when the normal distribution really is a good fit to reality, it's not too surprising that a method that uses and builds that normal distribution will do well. This is especially true if n is small. In this circumstance, if n is large, the two methods get very similar results, but if n is small, LDA usually does better. So maybe the main advantage of logistic regression is that it puts more emphasis on the decision boundary itself. And as an example of that, suppose you have points that are actually linearly separable. Then, just like a maximum margin classifier, logistic regression can always separate them. Assuming you find a point that's really close to the true minimum. And so let me show you a few examples of that. All right, here's a figure I found online that shows the two algorithms applied to the same data set. And so on the left, we have the data set in question. You can see there's a bunch of X's and O's. The other two figures, exactly the same data set. So these are not different data sets. They're just the same data set repeated 3 times. So let's look at a comparison between, they've put logistic regression on the left, and they've put LDA on the right. And if you look at the decision boundary, and you look at where the O's and X's are, one thing you'll notice is that these are linearly separable points, and logistic regression has actually linearly separated them. All the X's are on one side, all the O's are on the other side, just like a hard margin support vector machine would give you. On the right-hand side, you can see, well, we have fit Gaussians to the two classes, the X class and the O class. And when we compute the decision boundary, it does not do a perfect job of classifying the training data. We have some O's here that are on the wrong side, and we have some X's down here that are on the wrong side of the decision boundary. So remember what I said earlier, that logistic regression tends to give more emphasis to points that are close to the decision boundary than it gives to correctly classified points that are far away from the decision boundary. And one outcome of that is that it will always linearly separate linearly separable data. Whereas LDA does not do that. LDA gives every point equal influence. And so there's some points near the decision boundary that just stray over onto the wrong side. Another advantage of logistic regression is that in practice it proves to be more robust when you have distributions that really aren't very Gaussian. So when you're trying to fit a Gaussian distribution to a distribution that isn't even close to Gaussian, especially distributions that have a lot of skew, meaning that they're not symmetric around the center of the distribution, they're kind of one-sided, then logistic regression is just going to be smarter about separating those points because it's not trying to model each class falsely as a Gaussian distribution. And logistic regression is a better choice if you actually have labels that are not 1, not 0, but somewhere in between. So Usually we're thinking about probabilities here. If you want to regress a function to probabilities, and some of those probabilities are between 0 and 1, logistic regression does that very naturally. And LDA does not. All right, any questions about this? Yeah. Yes, logistic regression is more sensitive to misclassified data points that are far from the boundary. The place where that is, so the question is, where is that reflected in the math? The place that that's reflected is right here, though not in an obvious way, and you have to think about it for a while. But well, let's start with the easy part, which is the omega matrix itself. So what is that number going to be? S times 1 minus S. If a point is on the decision boundary, then this reaches a peak of 0.25. If a point is far away from the decision boundary, then one of those values is going to be close to 0, so you're going to get a much smaller number. So omega itself tells you how close a point is to the decision boundary. High means really close, low means far away. With that in mind, the next step is to ask ourselves, so once you plug that into here, how is that going to affect the step that you take, E? And that part, unfortunately, is harder to think about. I don't have a quick answer for you. But roughly speaking, points where that diagonal value of omega is high are going to have less influence on E. And points where it's small, far away from the decision boundary, are going to have a bigger influence on E. That's true as well. So y minus s is only going to be small for correctly classified points that are far away from the boundary. It's going to be reasonably big for points near the boundary and even bigger for misclassified points far from the boundary. Right. So yeah, there's a lot going on here, and it's kind of hard to sort it all out, I admit. But so I want to end this lecture with yet another thing pulled out of our grab bag of topics. This is kind of out of left field, but there is something called a rock curve. And it is used to choose the threshold that you're going to use between false positives and false negatives in a lot of real-world applications. And it does it based on actually empirically looking at your test data. So a rock curve is generally, after you have trained your classifier, you take your test set and you run it through the classifier with various different thresholds. So, like for instance, if you're doing logistic regression, normally the threshold is 0.5. If you have a point where the logistic is bigger than 0.5, we say that's in class C. If it's smaller, we say it's not in class C. But we don't have to pick 0.5. We could pick 0.7. We could pick 0.1. And so what we're going to do is we're going to try a bunch of different values of the threshold. We're going to go through all the different isocontours of our decision function or our regression function. Well, this is usually for a decision function. And for each of those different thresholds that we choose, we're going to plot a point. And once we've plotted a bunch of those points, they form a curve, which we call the ROC curve. ROC stands for Receiver Operating Characteristics. It's an awful name, but we're stuck with it for historical reasons. And a ROC curve is a way to evaluate your classifier after it is trained. And it's made by running the classifier, again, on the test set or the validation set. And it shows the rate of false positives versus true positives. So, what does that mean? All right, the x-axis is called the false positive rate. And it is the percentage of negatives classified as positives by your classifier. So in other words, test set items where the correct label is 0, but you said 1. And the vertical axis is called the true positive rate. And so that is the percentage of positively labeled test items that you classified as being positive. So they are in class C and you correctly classified them. And so that is also sometimes called the sensitivity. So to draw it another way, that vertical distance, that's the sensitivity. The horizontal distance here is the false positive rate. But 1 minus sensitivity is also important because that's the false negative rate. And 1 minus the false positive rate is also, has a name, it's called the specificity. All right, the way that we make this diagram, the way that we plot this curve, is that we assume there is a knob that we can turn to trade off false negatives versus false positives, to trade off these two types of error. Now, for our purposes, that knob is going to be the posterior probability threshold, where we say anything above this threshold is in class C and everything below it is not in class C. So we turn that knob, and for each, as we turn that knob from 0% to 100%, at each point along the way, we measure the classifier's error rate on the test set, and we plot these 2 points, or we plot a point for every setting of the threshold. Now, you notice there's a dashed diagonal on this thing. The diagonal has its own purpose. So the point at the bottom left of the diagonal is essentially corresponds to a classifier that always classifies negative. In other words, no matter what test point you give it, it always says that's not in class C. And the top right point on the diagonal corresponds to an equally stupid classifier that always says positive. No matter what test point you give it, it says that is in class C. The other points on the diagonal essentially correspond to random classifiers. So for instance, at 0.8, this would represent a classifier that says positive 80% of the time and negative 20% of the time, but it doesn't even look at the data you're feeding in. It just generates a random number and outputs the wrong answer. So again, the diagonal line corresponds to all the different possible random classifiers that do not look at the input before outputting some random label. Now, a rough measure of your classifier's effectiveness is the area under the curve. So for this curve here, for this curve here, what we do is we actually would integrate the area underneath that curve. And the closer that area is to 1, the happier we are. A perfect classifier would give you an area of 1. For the random classifier, you can see that the area under the curve of all random classifiers is 1/2. So you'd better beat 1/2. If your classifier's area under the rock curve is 1/2, it's a useless classifier. And so the main reason why I'm telling you about this is because in practice, if you want to pick a good trade-off between false positives and false negatives, in, for instance, your cancer diagnostic tool, the way we do it in practice is not by some theory figuring out what the numbers should be. The way we do it is we actually plot a ROC curve on real test data, and then we decide where do we want to be on this curve. And that's the right way to choose your loss function, your asymmetric loss function for something like cancer diagnosis. Any final questions? Yeah. It does not generally turn out to be symmetric at all, no. Nope.